least I'm going to try. All right, I have a series. In fact, I've been working on a book for years. This is what I'm going to call the book, and this is my series called Divine Design. It's all about mathematics and God's creation. This particular one, like I told you, I call optimal design. And it's special in this regard. This is the only one. You guys are kind of the only kind of class I can show this to because it has calculus in it. So I can't show this to general audiences because I can't talk calculus with most people, but with you guys I can. Just this idea of optimal. Who's the optimal? Without a doubt, it's our Creator. And so I always love this passage at the end of creation. The kind of the what? I guess you could call it the creation assessment. It was very good. And another passage that talks about things being optimal or really great. I love this passage from Philippians chapter 4, verse 8. You know, perfect example of what kinds of things we should study and talk about. Okay. A mathematician, I'm gonna show you a few mathematicians and give you some quotes about things being optimal or, you know, the best. This is Johannes Kepler, kind of a hero of mine. What I really think is cool about, well, first of all, he was studying to be a Lutheran pastor, and during his studies, he got really fired up about this, some of the science classes he was in. He wound up becoming, one of the most famous scientists ever. But Kepler never forgot his roots, and right in the middle of scientific research. In fact, he was actually presenting to the Royal Society in England. This is like what? Kind of like the conference of the top scientists in the world, where they would get together. They asked him to present, and he got there, and he was in the middle of his scientific data, and he would stop and break into praises to his God. And I'm sure some people thought Kepler had lost it, and just the opposite. Kepler, he really had it right. Anyway, you know, he's the one that discovered you and I are on an elliptical ride around the sun. He's the first one to really nail down the elliptical orbits. But here's what he said about optimal design in God's creation. Nature uses as little as possible of anything. In other words, we always talk, you know, right now the big talk is green. Let's do things efficiently. Let's save. Well, God's creation always does that. It's always doing things in the most efficient way. And we're going to talk about that today. And Kepler recognized that. A bunch of people did. This is a French mathematician who said almost the same thing. He said nature always operates with the greatest possible economy. And again, we're going to look at an example of how light does that today. Another one, Sir Isaac Newton, who's one of the guys that discovered calculus, he said, nature does nothing in vain, and more is in vain when less will serve. For nature is pleased with simplicity, and affects not the pomp of superfluous causes. A kind of fancy talk for, it really does things as efficiently as it can possibly. Leonard Euler, another pretty famous mathematician, said, because the shape of the whole universe is most perfect, and in fact designed by the wisest creator, nothing in all the world will occur in which no maximum or minimum rule is somehow shining forth. See the words maximum, minimum. Leonardo Da Vinci, the true Renaissance man, artist, scientist, unbelievable inventor. I'm sure you've maybe seen some of his sketches. Here we are in the Middle Ages, and he designs a helicopter. Guy was so far ahead of his time. And here's what he said about inventing. Human ingenuity may make various inventions, but it will never devise any inventions more beautiful, nor more simple, nor more to the purpose than nature does, because in her inventions nothing is wanting, and nothing is wasted or superfluous. So there's obviously some consensus here. The Center for Biomimetics in England actually has put out this quote: "Nature works for maximum achievement at minimum effort." It's another really good way to say it. And by the way, this Center for Biomimetics has its major purpose is to do nothing but to copy God's designs and make use of them for new scientific furtherment. That, by the way, that's becoming a huge part of science today. Copying, they don't call it copying God's design, they say copying nature. Of course, we know where that's from. This is just a picture. I know we didn't have, we should maybe flip the lights. And I should turn this one on here, because I see you don't get very good contrast. We didn't do trigonometry in this course, but in order to take this class, you had to have a little trigonometry, and you obviously spot here the sine curve or cosine curve. And the way they created this is they put a light on a spring. And obviously it was powered so we could see the idea of the light. And then they just started it bouncing, and then when it was bouncing, they had it on a slider and they just moved it along the slider. Well, this is the result, and it is the famous sine curve. The way sound travels, the way light travels, the way radio waves, the way television waves travel. Electricity is, even our temperatures fit this. I don't know if you've ever seen a plot of temperatures, for example, for the city of Milwaukee or whatever place for a whole year. And this is basically what you're going to see. It varies, obviously, each year, but the idea is, right now we're heading up, probably somewhere in here, spring, on the way up. And we're going to get to summer, and then we're going to be back in the pits of winter again. And then it keeps repeating, which reminds me of Genesis 3:22, when right after the flood, God promised to Noah, I'm not going to send another one of these until I come back again. And until then, the seasons will keep happening. And anyway, the growth of plants, everything seems to... So, and what do we have here? A max every time you reach the top, and a min every time you reach the bottom. And of course, there's all kinds of points of inflection up here too. Just another animated view of that famous curve. I didn't get any chance to talk to you about the golden rectangle, but I find this to be an interesting optimal problem. If you want to extend a square, you got the original square, and you want to add a square onto it, so to speak, to make it as big as possible. The added area is maximal when the golden section is used. And I don't have a whole lot of time to go into that, so I maybe shouldn't have put that in there. But anyway, golden rectangle, which is also another one of my presentations. It's all over in God's creation, and again, it's really optimal. Now, I'm going to just give you a simple concept. We have a line. The question is, where can I go with a light ray that goes through point A, bounces off the line, and goes through point B, so that the distance from A down to the line and up to B is the shortest possible distance it could be? In other words, the minimal distance. Well, it's actually a very simple mathematical solution. What you do is you find the mirror image of point A, And you can do that real easily with a compass. You know, get those two distances to be the same. You would probably remember how to do that. You take your compass and you make it bigger than this distance, and then you cut two arcs, and then you can find this point pretty easily with a compass. And I'm calling it A prime. Okay? So a symmetrical image of point A, and then just connect that point A, that A prime with B, and where it crosses the line, that's the perfect bouncing place, so that the distance in red is the shortest possible, literally the minimum path. I find it remarkable that something as simple that you can teach to like first graders, symmetry, is the key to the solution to this. By the way, we could have done it on the other side. We could have found the mirror image of B and connected it that way. Okay, so now I'm claiming that that distance in red is the shortest possible way you could go to get there. Not close, the best. Well, guess what? How could we check that out? We could do some calculus, and that's what we're going to do. Here's kind of the same situation. I guess I got A and B on the opposite sides, but it's the same thing. I just set up an idealized situation with some labels on it. I'm calling this distance X, this distance C. So what would this distance be from D to P? C minus X. Okay, now we're going to do just a little bit of math here. First of all, it should be obvious where I got b squared plus x squared equals bp squared. That's just the good old Pythagorean theorem on the triangle on the left, right? Okay, and shouldn't I be able to do the same thing on the right in the triangle on the right? Do you see where I got that c minus x again? Not everybody, maybe. This, from here to here, is c. And from here to here is x. Then doesn't this have to be c minus x here? Okay. So if you take that leg, square it, add it to the other leg, a squared, it should equal the hypotenuse, ap squared. Okay. Now, I think you'll agree, ap plus bp is that distance I claim is minimal. So what we're going to do is solve for, we're going to take the square root of both sides and solve for bp and ap. And now add them together. And I'm just, I don't know, why am I calling it t? I don't know. It's the distance that I'm trying to prove to you is minimal. Okay? How can I prove that's minimal? Well, we could take the derivative and set it equal to 0 and solve, something you guys have been doing quite a bit. All right. Well, I rewrote the square roots using the power 1/2. Nothing special going on yet. Now it's time to take the derivative. Well, you guys know how to take the derivative. I have to first use the power rule, bring the power down 1/2 times that thing, and then lower the power by 1. And you see where this came from? Chain rule. Isn't that what this is too? I mean, after you do the power rule, don't you have to take the derivative of what's inside? And this is a constant, that's why that doesn't appear. That's a constant. Here we do have a variable x, so I have to multiply, the derivative is 2c, and this derivative is 2x. So anyway, chain rule, okay. So we got our derivative. Now, I just rewrote it, or I copied it, and let's set it equal to 0. Now, maybe you don't see how I got it in this form. You know that anything to the negative 1/2 power means what? Square root in the denominator. So I just stuck that down below in a square root, and I stuck this big old guy downstairs under a square root. Okay? And I set it equal to 0 because I want to find where the max or min is. In this case, the min. All right, so here she is. We could what? Just add the right fraction to both sides, giving us this. Now I'm going to make some key substitutions. Let's see if you can tell what I did. In place of the square root of b squared plus x squared, I wrote bp. Okay? Isn't this equal to bp squared by the Pythagorean theorem? And what's the square root of bp squared? bp. And likewise over here. So now this looks a lot simpler. In fact, this looks more like a geometry setup. Now I have a proportion. And in fact, that's the key thing. What does that mean if those sides are proportional? You can rewrite the proportion. It's basically telling you the two triangles. I mean, there's a little bit more work that I haven't included here, but you have to do what? You have to prove the sides are proportional and the corresponding angles are congruent. I didn't do the angle thing, but we really have gotten to the point where they're similar. And if they're similar, what does that mean? The corresponding angles have to be equal. Okay? And so what it's saying is if that distance is the lowest possible distance, then this angle will equal this angle. And of course, that's a famous science thing. How did you learn it in science class? The angle of incidence equals the angle of coincidence equals the angle of incidence. Remember that in science class? So when light reflects, it creates an equal angle where it comes in and where it goes up. And sure enough, that's the way light works. So light works in this optimal way. And this is just a picture of light reflecting. And there's exactly what happens. Whenever that reflection takes place, that angle has to equal that one. And I've just proved to you this distance will be minimal. So once again, light travels the most efficient way it can. However it gets to the object, it will take the shortest possible path. That's exactly the kind of thing calculus teaches us. When you dip mathematical skeletons in soap solution, the soap film will automatically go to the minimal configuration. That is, it'll hold the most volume for the least surface area. It automatically knows the calculus behind it. And this gets fairly complicated. You wind up with some really intricate indentations. But soap knows how to do that immediately. By the way, not just soap. You can also do this, by dipping in certain kinds of water too. The whole thing is. But anyways, interesting how God's laws know how to do this immediately. Here's the reason I have this up here. There's a very famous conjecture called the Honeycomb conjecture that's been around for a long time. And not that long ago, 1999, Thomas Hales, the University of Michigan, has finally proved it. And what he proved, in white, bees have discovered the most efficient way of dividing the plane into equal-sized cells. Not like really good, but the optimal. Again, interesting how God's creation demonstrates this over and over. And by the way, that was proposed way back in 1953, so it took, 46 years for this to be nailed down. But it's now been nailed down. Hales shows that no curvy side cells could do the job any better. And that was the only thing left in the proof. Most efficient means precisely that any other design for covering the plane with cells of the same size will require a greater length of walls. So that's the most efficient it could be done. Here's actually the front page from his proof. I'm not going to go through the proof, but you see it says, this paper gives a proof of the classical honeycomb conjecture. Any partition of the plane into regions of equal area has perimeter no less than that hexagonal tessellation that nature uses. just to show another interesting thing about the hexagon. If you take a bunch of spheres and put them on another sphere, which is what this is trying to show you, a bunch of little spheres packed onto a big sphere, and then when you look at it more closely, and if you really, kind of crowd them in, what happens? They become regular hexagons. Just interesting how that always works. So if you took a bunch of circles, put them in a network, and then just kind of squished them, put pressure on all the sides, this is the kind of thing that will happen. It right away knows to go to that most efficient configuration. This is not very good, but I tried to make an animation showing you how that scrunching works, and it didn't work out like I wanted it to, but that's what happens. It winds up being a regular hexagon. Interesting comment on this. But the bee's skill in solving problems in maxima and minima does not end here. It was found on examination that the angle formed by the faces of the steeple, now this is kind of hard to explain, but in a honeycomb, not only do you have the hexagonal opening, but when you go down to the bottom of those tubes, they come to what they call a steeple. They come to a point down there, like a polyhedron, a 3D. And that's what it's talking about. So the angle formed by the faces of the steeple with the axis was such as to make the total surface for a given volume a minimum, a result experimentally determined by a mathematician by the name of Maclaurin. What clever bees. Well, what an amazingly knowledgeable creator. This is just showing kind of an interesting, another maximum situation with graphite atoms and how they too use this hexagonal shape. Another interesting little tidbit for bees. Just going to hit a couple things here. This article I read was called Honeybee Calculus and the Analytic Geometry. Look at the white text. It's known that a honeybee returns to the hive and performs a dance to tell, I don't know, I'm sure you're aware, the scout bee goes out and finds good sources of pollen. They will come back to the hive, and then they literally tell the other bees in the hive where the good stuff is. And then they all take off and go there. And now when I say tell them, no, they don't do it audibly. They actually do a little, they call it the waggle dance. And in that dance, the bee will rotate and kind of shake its booty, so to speak. But what it's actually doing, the angle that it goes tells you what angle to take off on, and how far it backs up tells you how far away it is. And by the way, that's called polar coordinates. Some of you may have done that in your pre-calc class. Polar coordinates. So instead of x, y, it's a certain angle, and then go out a certain distance on that angle. It works just as well. Anyway, this is so accurate that they actually built a robotic bee that goes into the hive and does that dance. And so they actually can control where they want to send bees. So on a computer, they'll say, give them these coordinates. Write it into the computer. This little bee, this little mechanical scout bee does its dance. All the bees take off and they go there. You can literally tell bees to go where you want to. They thought they'd be clever, and they gave the bees the coordinates for the center of a lake. Now let's see what they do. The bees never even took off. You know, it's almost like you could just see them there going, duh. We go for plants. There are no plants in the center of a lake. Why are you sending it? But the cool thing is they actually knew. They had some kind of a map up there. And they're like, no, I'm not going there. What do you think I am, dumb? No, it's just unbelievable, the cool mathematical coordinates and things that are built in. Toward the bottom of this, it also says, how does the honeybee, how do they know how far they've gone, that they've gone the right distance? They now have proved in experiments that bees actually know how to do this by integrating. By the way, integrating is the inverse of finding the derivative. They actually integrate the speed by how fast images pass by their eyes. They know because they've set up an experiment where they control the stuff on the sides, and it's really cool. So bees use all kinds of calculus. Other kind of cool coordinate things. The leatherback turtle is kind of an unusual guy. Their bodies are kind of teardrop shaped, and turns out that they have 7 ridges along the length of their shell, which basically optimizes them being able to slide through the water. They now know because they've mathematically analyzed them. Okay, let's go inside of a vein. Blood pumping. Engineers know that in order to get the best flow of a liquid, doesn't matter what, but such as blood, a pipe's cubed radius must equal the sum of the cubed radii of each of its branches. That they know from experience that works the best. And guess what? That's exactly the relationship found inside of you and inside of living animals. Blood cells, how are they shaped? Guess what? Optimally. Let's see, bottom line, middle of the page. The biconcave shape that red blood cells are in, naturally form for this area, so the volume ratio, because it requires the least energy. So once again, optimum efficiency for the blood cell. And it tells later, up here, it talks about how you really need to have increased surface area in this, and it does that. All right, let's talk about the parabola just a little bit. We've got this grinder. Of course, every spark has to travel in a parabola. It's just the way gravity works. And as you know, there's a height. Usually a parabola has an optimal height. I find this kind of interesting. Look at this. They were experimenting on different shaped nose cones for aircraft. And this graph kind of shows what? The drag. And you notice this blunt thing, of course, has terrible drag. It's way up high. Then they went with a cone. That did better. Not as blunt of a cone did even better. A hemisphere was even better, but the parabola was the best. And again, here's another one. What's the perfect geometry shape so that you make a mirror out of it and all the rays come out parallel? Answer? Parabola. Every one of your car headlights has a parabolic reflector in it, because all the rays will come out parallel then. If they're not parallel, they're crisscrossing, you won't get much light. So what will give you the maximum light from your flashlight, from your headlight? That parabola shape. So another optimal thing that's just built in. Okay, now this is a chambered nautilus, but it's the shape I wanted to talk to you about, the logarithmic spiral. Leonard Euler proposed that tracks curved in a logarithmic spiral were optimal for slowing and turning trains in rail yards. And in fact, guess what? This is basically the optimal shape for exit and entrance ramps on freeways, which is what kind of the left illustration is telling you. Of course, you can't beat a sphere. The sphere has got what? Optimal volume for minimum surface area again. And so the sphere comes up repeatedly in God's creation. Bubbles, water. You and I, when we're first conceived, are spheres. But especially, the water droplets is the way we see it. But here's a surprising one. Slime mold topology. This simple organism has the ability to find a minimum length solution between 2 points in a labyrinth. Watch. Okay, they literally give it a labyrinth, and what are they again? Slime mold is put on one end, and then they put the prize on the other end, and the slime mold has to find its way through the maze to get the food. Okay, that's the idea. And at first, they're all over the mat. Okay, as you can see by kind of the gold. But then what happens after a while is they start narrowing down their paths. And eventually, they got it. They got the minimum path. It doesn't take very long either. It's, what does it say, 8 hours after the introduction? So here we're talking about a really low-level form of life. And guess what? It's got this minimum thing built in again. This incredible efficiency. I just find that amazing. How about ropes? Well, there's an article called Nature Knows Knots. I guess ABC News. I like this. Tall ship sailors are adept at storing ropes, but nature does it better. Sailors leave a lot of unused space in between their rope coils. New mathematical analyses show that the helical twists of DNA and proteins are the ideal coiling shapes. They do it much better. Yeah, they ended up by saying evolution has already built the, they say, well, yeah, give it a couple trillion years and nature kind of figures it out by default. And we know that right away when you said let there be, all this fantastic stuff was built in. Here's a really surprising thing called liquid logic. Did you know you can solve problems with water? Here's the concept. The idea of problem solving with liquids is not as bizarre as it might seem. Some geologists believe that water flowing over rugged terrain spontaneously what's going to happen if you pour water over rugged terrain? Well, of course, the water is going to find the low spots, right? We know that. Simply because of how gravity works and how water likes to disperse and be as level as it can be. Anyway, it right away organizes itself into a river network that minimizes the rate with which the flow relinquishes gravitational energy as it moves downhill. So, would you believe optimal solutions from just the way water disperses? Really cool. Actually, I guess you could call it water calculus. And when you get into the divine proportion, I don't know if you guys have ever heard of phyllotaxis, but phyllotaxis is the way plants organize their branches. And it's really a cool study. I don't have time to tell you about it, but I wanted to just show you this. Here's an example of a sunflower and phyllotaxis. You should be able to see that the little florets inside the flower form two sets of spirals. There's one set kind of going clockwise, and there's another set coming around counterclockwise. Anyway, that is no accident. It turns out that the way those are set up, the way God created that will allow each one of these little nodes to get an equal amount of light and moisture. And so it's like perfect sharing. And there's no snubbed part of the plant. Really cool. Maximal again. Or what does it say here? Fibonacci spiraling is a result of the system keeping the energy required for the growth of its parts to a minimum. Optimal design in human hearing. As you can see, they're studying this at Carnegie Mellon University in Pittsburgh. Scientists there have discovered our ears use the most efficient way to process the sounds we hear, from babbling brooks to wailing babies. And I'm not talking stuff that I'd like. I mean, these are all from science publications that this information I'm giving you. This is going to shock you. You want to improve your network, your computer network, or your internet connection, or the network on campus? Take a look and study ants. Ants are incredibly efficient. again, similar to that slime mold. You give ants a food source and where they are, and they will very quickly determine the most efficient path to get there. And we actually, would you believe, learn better computer networks from watching them. You notice this is not that old either, fairly recent. This is a shocker. I don't know how much you know about fractals, but a fractal is something that, when you look at it closer, has even more detail. Well, it turns out that coastlines are fractals. That is, if you look at a section of coastline and where it meets the water, obviously there are jagged edges, right? But then if you move closer, you see even more jags that are tinier. And then if you move even closer, you see even more. And if you move closer, you keep seeing more and more. Well, it turns out that this fractal, which is a mathematics topic we haven't had a chance to go through, it turns out that they've just proved this. Fractal coastlines are best at damping waves. By damping, we mean calming the waves and not having, what? Minimizing erosion. And so in other words, as these big waves come in, how do we take the the impact and have the least damage, that is, have the land not what? Erode too much? Answer, the way God does it, fractal coastlines. Here's another one, Graham Taylor, University of Oxford, UK. Swimmers and flyers from insects to whales all cruise at the speed that lets them slip along most easily. And they're studying this quite a bit. And you've ever heard of phototropism, but plants will grow toward the light. You probably know that. So if you put a plant, let's say, in a room where there's a window, the branches will like lean toward the light. That's called phototropism. Anyway, key feature of living organisms is their ability to adapt their environment and external stimuli. In the case of plants, they grow and bend in the direction of light in order to achieve maximum benefit and efficiency. Okay. Guess that's pretty much it. I got a couple more things, but they're actually. So anyway, while I'm teaching all of this stuff about finding out, maximum and minimum, I'm kind of bursting wanting to tell you about all this other stuff. At least I have one chance to show you some of that. It's pretty cool. So, God's creation, I guess you could say, uses a form of calculus all the time. It's always going for this maximum efficient thing. And, again, the evolution